Yeah, so good afternoon, everyone. So indeed, let me briefly introduce Professor Patrick Peter. So Patrick is a director of research at the CNRS, which is the French National Agency for Scientific Research. He works at the Institute for Astrophysics in Paris, and he is in fact the deputy director of this institute. So Patrick has worked on a large variety of topics related to the physics of the early universe. In particular, he is of course very well known for his numerous contributions on topological defects, but he has also been involved in many other topics, for instance, quantum cosmology and alternatives to inflation, among which are bouncing models, the topics of his lecture at this school. So Patrick, thank you very much for having accepted our invitation. And if you are ready, you can start.
Okay, thank you very much for the invitation. I'm very happy to give this set of lectures that I might try to remember a couple of things now. And I'm just very much unhappy that I do not, here we go. I'm just very much unhappy that I'm not live with you in Chennai, which I haven't been, which I've not had the pleasure to visit yet. So anyway, so I'm a little bit disappointed to be alone in a CD room in front of a screen. So please do not hesitate to interrupt me and ask any question you may, because it's probably going to be easier for me if I have some sort of interaction rather than speaking bizarrely in a room. Right, and if anything goes wrong, like if the sound stops or something, please do tell me as well, because I have no clue as to what is happening. Right, so as I wrote, yes? Okay. So as I've been introduced to, I'm supposed to be giving you some lectures on bouncing cosmologies, and I should have written like bouncing cosmologies rather than bouncing cosmology, because even though we know that there is only one cosmos and therefore it's only supposed to be unique, there are many models. I will try to discuss that a bit, but so let me first explain a bit what I am going to discuss. First, I will introduce the whole thing by first reminding you ordinary cosmology, standard model plus a bit of inflation, just to be able to understand in what kind of framework bouncing cosmologies are set up. And I will also use this opportunity to introduce the notations I will be using. And right, plus the general framework, right? Then I think I will introduce, I will make like a tour of all the known, not all the known, of course, bouncing cosmologies, but I will make like a tour of bouncing scenarios. And then I will have the pluses and the minuses, of course. What is good in bouncing scenario, what is not so good in bouncing scenario. And then I will end up with some predictions. And of course, comparison with observations, basically. So that's roughly the general framework of what we will be discussing in the coming days. And I'm really sorry, I have only one board. So basically, as soon as I write something, I will have to erase it, which is a little bit silly, I reckon, but I couldn't think of any other solution. Sorry. So anyway, so let me first start with my introduction. And first, I really want to emphasize, because sometimes people see lots of...
Patrick, I'm sorry to interrupt. This is
yes,
Sriram.
Sure.
Can you just improve the focus? I think people are having some difficulty in seeing. Will it be possible to adjust the focus?
I'm not sure I can do anything about that, unfortunately.
Okay, maybe move it slightly forward.
Hang on, let me see.
Shantraj, can you tell us?
Yeah, sir. Okay. So there is a video settings is there, the bottom.
Yes, right. You're right.
Just adjust for auto low light. This option is there.
Is it better?
Yeah, I think so. It's better now.
But then I will have to
Just write something, sir.
pick it up a little bit closer. Hang on. Assuming there is no wire that prevents me to doing that. Is that better?
Yes, sir. Now it's better. Yes, now it's better.
Okay. Now let me say. Did it change anything for you right now? Can you still read?
Shantraj, can you?
No, sir. Just you need to try to adjust it.
Sorry?
Can you go to the video settings?
Right. Okay. You can't read it, right?
Video settings, and there's an option is that adjust for low light. Just click the mark, tick mark.
Okay. Right.
Adjust.
Which one is it?
Yeah, it is changing, Patrick.
Yeah.
That's the best I could do.
Just click that. I mean, click that. Just click that one. Professor, can you enable that auto for adjust low light? Adjust for a low light.
Yes, but I am at the minimum.
Okay.
I can. Maybe.
Yeah. Now it's okay. Now it's fine.
Now it's fine.
Yeah.
I can read everything.
Yeah.
Let me try to again get it a bit closer.
Yeah.
Sorry, this camera of mine is pretty bad. So
yeah. Now it's better. Yes. Now it's better.
Okay.
Yeah. Thank you.
So what have I done with my paper? No. So here it is. Okay. So the first thing I wanted to say is that before we discuss any changes in the standard model, I think it's cool to remind oneself that the standard model we are working with, which is the hot Big Bang, is really absolutely amazing. And we need also to remember that it did not even exist 100 years ago. So it's a beautiful model which explains a hell of a lot of data, and which is, it's really brand new. So trying to find alternatives and to put it in its corner or whatever is already, one has to remember how impressive it is already. So we have, first of all, we have the expansion, right? We have measured the recession of galaxies and things, and we know that there is an expansion. This is sort of proven, of course. Then you have the CMB, and then there are a lot of other things like cosmological constant, which, even though it's not very pleasant for many people, it actually is part of the standard paradigm, or in a sense, it can be integrated into the phenomenology of it. Then we have the light element, right? Hydrogen, helium, and all that, all the abundances. And of course, finally, large-scale structure formation, which is, so before we move on to doing anything else, we have to make sure that we reproduce all these beautiful things, noting that all these things are quite related with one another. We pick up the initial conditions in the CMB to start the large-scale structure formation and all these kind of things. So everything is kind of rigidly fixed. And it is really amazing that we can do anything at all about that. It's a working phenomenological description, which is amazingly good from, I don't know, a very small fraction of a second after the Big Bang, up until now. So we have to remember that even before changing anything. Of course, there are some issues as well, right? And so in particular, we know that the spatial curvature, I will go on to the notation later, but I want to have a general introduction. We know that the spatial curvature is essentially vanishing, which is a first problem. We have a question of relics. I may discuss that later if you're interested in, coming from ground unified theories, coming from supersymmetry theories, coming from high energy theories, essentially. That's really a high energy question, but it does not really fit in the overall thing. And then, as I said, we have the CMB and its fluctuation, which explains pretty well the large scale structural formation that ensues, but we don't know what really the seeds for the CMB are. And of course, I mean, we know, some people think they do, but it's not really clear. I mean, it can be different what we think. And then there is, of course, the initial singularity, which, given the subject of my lectures, is going to be central to whatever I will discuss. Right, actually, this initial singularity is the reason why there is a tiny horizon. And that's getting into the line of all those usual problems. So all these things are often proposed as a good reason to justify, the paradigm of inflation, right? Because indeed, these puzzles of the standard model find a natural explanation in the framework of inflation, but not necessarily the whole thing. I mean, at least there are, the inflation provides a natural solution to these things. There are other issues which are completely beyond the scope of these lectures, and I don't even know if you are planning to discuss those, but questions like baryogenesis, for instance, which may be having to do with the relic, and it's also a high energy thing. Right, so we have a global image of a working phenomenological theory with a few issues for which there is already a paradigm that explains everything. And indeed, I should even change this title again into bouncing cosmology paradigm, because what we're trying to do with these models is to replace inflation with a new paradigm that will be based on a bounce. And I'm saying really replace, because of course we can always imagine to have a bouncing cosmology followed by a phase of inflation, but that's not exactly what we aim at doing. Of course, the more complication you have in your model, the more data you are supposedly able to explain, but it's not that obvious. So, but anyway, now once you have this overall setup, I'm not sure you can see here, yes. Once you have this overall setup, you find that inflation has some problems of its own, right? So, because at some stage, don't take me wrong, I'm not trying to defend inflation because otherwise the purpose of my lectures would be silly. But inflation has some problems, and in particular, like you have these how should I write that? Super Planckian issue, trans-Planckian problems. I'm not going to enter the details of this thing, eta problem, inflation, but also the singularity, which is somehow still present in these models, in the sense that the underlying models are not geodesically complete. And therefore, so you may be tempted to say, well, inflation never claimed to be able to solve this issue. And indeed, they never did that. But still, it is an issue which needs to be given attention to. Right, so basically, you see, again, it's already the second time I write singularity, and I'm really much into the singularity issue. So let me, again, draw the general idea, which is the following, very rapidly. If we stick with general relativity, and we have the universe as we know it, which is full with perfect fluid, radiation, matter, and all that. So we have GR plus, say, ordinary matter. It doesn't seem to be any way out, and I will discuss that later, to the following. When you write down as a function of time the scale factor, basically you measure that, and what you find is that you have something that is over here, say, and then when you go backward in time, eventually there is always a place where A goes to 0, which is the singularity. Of course, there are not so many ways to escape that. There are essentially two ways. One of them is to do, that. You go all the way to either a constant here, or all the way to 0 if you want, as long as it takes you an infinite amount of time to go to 0. Or if you don't go to a constant, well, you can just go up again. And that is, of course, a bounce. Note that, and I will be discussing that not in full details, but just to show sometimes you can have this behavior for the scale factor, and yet you can interpret that in terms of a bounce when you actually measure distances. This is the scale factor. This is not necessarily the distances which you measure. Right. So, of course, what you really want is to get rid of that. This is not good. So I'm saying that because there are some bouncing models, I will discuss that later perhaps. There are some bouncing models for which there is a singularity, and I honestly don't really understand the point of having a singular bounce, really. Now, there are issues, even when you get rid of this thing, there are issues that, first of all, you can ask question, are the conditions for that, for a bounce. As I said, if you take GR plus ordinary matter, and you look at the phase of the current phase of expansion, you know that you will end up to a singularity. So it seems that already, even before making any calculation, after I said that, the conditions for getting a bounce are not going to be that trivial, obviously. And in fact, indeed, as soon as you implement these conditions, you find some instabilities. And they are crucial in a sense because they explain why at the moment most of the cosmology community still think that the relevant paradigm for describing early universe is inflation, because there are many issues. So another point is, of course, so I think David may have gone to that already, but the idea is that we don't want to look only at the background, we want to look at the perturbations, and normally perturbations are produced like in a phase of contraction, and you want to pass them through the bounds. So you have to understand what's going on with perturbation through the bounds. And this is not a very simple question. There are matching conditions and things like that. And finally, I'd say last, but certainly not least, is implementation. So implementation in a working theory. And actually, at this point, I'm not sure that bouncing cosmology is not a little superior to inflation, because inflation very often is not really taking the existing fields, they just add some extra field in the framework of, say, ground unified theory or string theory or whatever, and it's not 100% sure that it's not actually better to perform a bounce or actually simpler. So in particular, you want to implement that in accepted theories, and I mean, more or less, okay, that will be string theory, for instance. But you see, what happens is that in general, you have GR and ordinary matter. And more often than not, what you have to do is you have to modify your theory of gravity. And very often, and I will take this specific example, and one of the reasons why I will take this specific example is that I know it better. It's easier for me to explain things I know better, which is when you want to quantize gravity. Right, so that's the framework. We know that the model is working. There are alternatives to the ordinary general things. Inflation may have issues. Let's try to get rid of the singularity first. And as I said, no one prevents you from getting rid of the singularity and then eventually initiate a phase of inflation afterwards. It's not impossible, but as I said, I want to restrict attention to the simplest case where you're back to non-accelerating solutions. Right. Okay, so now, as I said, I will first introduce my notations. I said that I introduced GR and the matter that I'm looking for. So the notations that will be in most of the cases, except in some examples from specific cases, but in most of the cases, I will consider the four-dimensional space-time whose dynamic is given by general relativity. So I will have the action being C4 over 16 pi Gn. I write it nicely because I will get rid of it in a minute. So minus G d4x, and I have okay, minus 2 lambda, why not? Plus an action for matter. Right. So that's the general framework. First of all, the lambda term will be plugged in the matter term because somehow you can interpret it. So I will just concentrate on the purely geometric side of it. Where is it? So I will just have that, and that includes now lambda, right? And we know that when we do that, we end up with Einstein equation. I will not define any further. I guess, I hope everybody knows the whole thing. G over c to the 4 t mu nu. Right, so that's the basic framework, really. And of course, I will start with the Friedman-Lemaitre-Robertson-Walker metric, which is for the geometric part, which implements homogeneity and isotropy in general. So I have ds squared equals minus dt squared plus a squared depending on t times gamma ij. It's just to set the conventions, right? So this gamma ij, you have various ways to write it. It can be either delta ij over 1 plus a quarter of k. Here is the spatial curvature, and then I have x squared. With a little arrow will be what is used, which is normally the bold mat in LaTeX, but I don't have bold mat on the blackboard, so I will use little arrows. Or, so this is in Cartesian coordinates, but you can also write it on the form of d in spherical like coordinates, 1 minus k r squared. This is the same k, of course. It's r squared, the omega squared. Right, so when it's left only with the scale factor, whose behavior I was interested in. And then, of course, the curvature here, which is also going to be extremely important, is k equals 0 or plus or minus 1. Yes, Saram? Oh, sorry, I thought you wanted to say something. Fine.
No, I didn't say anything. Sorry.
Oh, sorry, because all of a sudden my screen changed and your name appeared, so I thought you were about to say something. Sorry. Okay, and to simplify things, basically all these factors are, for the most part, irrelevant. So I will use units in such a way that h bar, which I haven't introduced, but you all know what it is, h bar equals c equals 8 pi gn equals 1. Simply because the calculations are simpler with that. So within these units, the Planck mass, which is 1 over square root gn, right? So this is dimensionless, of course, with these units. Right. So long for geometry. So as I said, the framework is first geometry, and then now the second part is matter, the matter content. Let me erase everything and go on for the matter content. While I'm erasing the bold, please feel free to ask anything. I know at the moment I'm being a little bit slow, and everybody knows everything I'm saying, but as I said, it's just a matter of stating the conventions, essentially. So for the matter, as long as you're interested in the background, it's very cool to stick with a perfect fluid, which consists of an energy density and a pressure, which is led by a time-like vector, right? And so this is time-like, that's u mu equals -1, as I said. And once you put that into Einstein equation, which I very cleverly just erased, you end up with a set of equations defining the Hubble scale by a dot over a, and the dot being a differentiation with respect to time as usual. You end up with the Friedmann equation, which are k over a squared equals a third rho. And then you have h dot plus h squared, which is a double dot over a, and that's -1/6 rho plus 3p. And so you see immediately here that if you want to have a phase of inflation, as I will discuss also, phase of inflation is a double dot positive. That implies, because there is a minus sign here, that implies that rho plus 3p is negative. And I think rho plus 3p negative implies a violation of the so-called strong energy condition, which is not too difficult to achieve, as I will show in a minute. Right. I completely forgot to mention in the previous slides, even though it's not an actual slide, that we will, of course, make a lot of use of the conformal time, which is simply defined by d eta, a d eta equals dt, right? So that the metric at the end, you end up with ds squared, which is a squared, now depending on eta, times an overall thing, which is minus d eta squared plus gamma ij, sorry for that, xj. Right. So if you use this scale factor and you define this curly h as being equal a prime over a, and the prime meaning a differentiation with respect to eta, these are very standard conventions anyway, you end up with the same Friedmann equation, which are h squared plus k now equals a third rho a squared, and h prime equals -1/6 a squared rho plus 3p, with of course the same remarks applying. Right, so that's all plain and simple. And now, so this is the fluid put into Einstein equation. Now the matter itself has some dynamics, So the dynamics is that d mu T mu equals 0 in principle. Again, all these hypotheses can and will be changed, but the general framework will be that. And that gives automatically rho dot plus 3h rho plus p equals 0. And you can replace the dot by a prime and then the standard h, a straight h by a curly h, and you get exactly the same equation, of course. And now, usually, to complete the overall description of cosmology, you have to tell what is the equation of state. And usually you're saying that P equals W rho. Actually saying that is not saying anything at all, because W can be any function of rho you want. And you know that if W is 0, that's pressure, that's dust dominated universe. Rho equals a third is radiation domination. And but you can have basically anything you want. And once you have put this into this particular equation, you can solve it in terms of the scale factor by replacing dA by dt, and there is a dA here. And then you can find that the initial, the energy density now behaves as exponential -3 times the integral 1 plus W, now possibly depending on A. And then you have a d log A, which, as you know, is W equals a constant, goes to A over, well, goes to proportional to A to -3, 1 plus W constant. Right, that's very common. Now, the last piece of information we're going to need is that this description can also be applied if matter is a fluid with such an equation of state, but it can also be a little bit more complicated and involve, say, for instance, a scalar field. And if I do that with a scalar field, I end up with, okay, so the canonical Lagrangian for my scalar field will be -1/2 d phi squared minus whatever potential. And this d phi squared is simply g mu nu, d mu phi, d nu phi. And now, from this Lagrangian, we can define, so the stress energy tensor now is -2, okay, dl by d g mu nu plus l g mu nu, and sorry, that was here, here you go. And when you apply that to this Lagrangian, you find d mu phi, and there's a minus sign, -1/2 d phi squared plus v, yep, g mu nu. Right, so this is, if you want to put that in the form which I just wrote earlier in terms of energy density and pressure, you just say that because the universe is homogeneous and isotropic, then phi depends only on time. And because phi depends only on time, you can rewrite d mu phi equals phi dot u mu, no, thereby defining the time-like vector. So you take that, you put it into here, and you end up with the actual form, the usual form, but now you will find that the energy density is 1/2 phi dot square plus v, and the pressure is 1/2 phi dot squared minus v. And that's where you see, for instance, that this is very much used for inflation, because if you, I said that I wanted to violate the strong energy condition, which is rho plus 3p, which, as you can see, is that's anyway, that's 2 phi dot minus v, right? And if you have a situation where phi dot is small, sorry, phi dot square. If phi dot square is smaller than d, then these can be easily negative. So this is the way to implement things. Right. So that's just a general
Patrick,
setup.
maybe we can check whether there are some questions.
Yes, sure, go ahead.
Absolutely. Can I, can I request you to come forward? If you have any questions, you can raise your hand. Are there any questions?
I would not expect any question at this point, but please go for it.
Okay. Yeah. All right. There are no questions as of now, Patrick. Please proceed.
Okay, good. Okay, so it's cool because now I will come to the overview of models. Overview being the word I was looking for earlier. And now within this framework, we can already start working. Sorry it took me so long. So overview of models. I will first discuss the models and then show how you can implement them and all that. Now, as I said, most of the models are based on GR plus some semi-classical components, which are usually scalar field. Which is why I introduced all these things. Now, of course, it can be some extension of it. Very often, if you perform a standard extension to GR, you end up in the previous framework by switching by a conformal transformation and all that. So basically, this is kind of a very general framework. But there is another category of models to which I will probably concentrate a bit more today, which is where you want to get out of these things, so you can stick with this semi-classical or even quantum or even fully quantum scalar field, but then you want the whole thing to be quantum. So quantize gravity, and that's what I want to concentrate upon today. And the origin, and actually this is the original idea of bouncing scenarios. I mean, the modern view of bouncing scenarios, which are the so-called pre-Big Bang models. So that was the pre-Big Bang models proposed by Veneziano and Gasperini quite some time ago now. And the idea is actually quite simple when you think of it. The idea is the following. When you look at what happened at the beginning of the 20th century, where people were using electromagnetism to calculate the radiance of a microwave oven, basically, which happens to be that anyway, but for really an oven, which is a so-called black body, basically, and as a function of the wavelength. And what was found is that the electromagnetism of Maxwell theory, you will calculate the radiance of the closed oven, and you will find a divergence. Right? That's, I think it's called Wien's law or something like that. So anyway, there is some divergence. It's not very clear on my drawing, but it goes all the way to infinity. And in particular, the integral of that was infinite. So you were saying that I lambda, actually, was going to infinite as lambda was going to 0. And of course, the integral as well. And that was a catastrophe, the so-called ultraviolet catastrophe for smaller wavelengths. And we all know what happened then, is that Max Planck arrived in 1900 and said, well, maybe the real law is actually that. And now the integral is finite, the energy is finite, you don't have that anymore, but at the expense of adding an h bar here. And that was the beginning of quantum mechanics, as we all know. So now, of course, when you look at, as I said, when you look at as a function of time now, rather than a function of wavelengths, but when you look at the scale factor, well, the scale factor, as I said, goes all the way down, like that. But when the scale factor goes down, forgetting about curvature for the moment, you know that h equals A dot over A. And you see that normally when it arrives with a non-vanishing derivative. So A dot is just a number, but A goes to 0. So A goes to infinity, but A going to infinity now, as I said, H squared equals a third rho, means that rho goes to infinity as well. So if you plot on this same diagram, if you plot the energy density, what you find is something like that, right? Sorry. And that's going to infinity, right? So it's exactly the same kind of idea. So you may be tempted to say, well, okay, let's extend that a bit. And instead of going all the way to infinity, what happens is that I will go all the way down again, doing the same thing by introducing H bar in the theory, which is originally completely classical, which implies that your scale factor has to do something else. If you want to, of course, you're not going to follow these equations anymore, but still, basically what will happen is that or that. Again, the two options. So actually, if you accept the notion of what happened at the beginning of the 20th century to be the same as what happens here, well, then you are naturally driven to quantize gravity to solve the Big Bang singularity problem. So that's what I will do a bit because I think it is quite fun. Let me, if you don't mind, quantize gravity. There are a couple of models that do that. Of course, there is string theory. I'm not going to expand on that because I'm not an expert on string theory. But there is one way to do that, which is the simplest possible way, which is merely to canonically quantize gravity, which is what people do in general, which is you take a theory and then you apply that, you quantize that a la Dirac, basically, and then you have a quantum theory and then you look at the consequences. And let me go through that a bit first, because I think it's, as a paradigm, it is very well defined. It's quite nice, and it's also what I'm working on. So I feel more at ease to speak about it. So let me just quantize gravity quickly and show how it solves some of the problems we were discussing. And by the way, Gasparini and Veneziano were doing the same using string theory. The pre-Big Bang idea was really based on the string theory. So if you want to quantize the theory, you need to have a Hamiltonian formulation. So you need to break covariance of general relativity, which is not so much of a problem because, in fact, when you think of it in cosmology, that's already what we are doing. We are assuming, after all, that there is a time, preferred time, that's actually an issue, but there is a preferred time in which we evolve. That's the cosmic time, right? So we already have this idea in mind that basically the universe is a pileup of, your four-dimensional space-time is a pile of three-dimensional hypersurfaces, which I will label sigma with a t for the time index, and that would be sigma t plus dt, say, and I have a whole stockpile of them. And so to set the notations, I take, say, a coordinate line, right? So that will be x I equals constant, right? And when I go from one leaf to the next, I have the following. So let me see. So basically here, right, so here I would have dt as I indexed here, whereas here I would have d tau, that would be the proper time along this line, which in general is going to be called n, which is an arbitrary function of whatever you want, times dt is just a shift, it's just a lapse between the time, the external time and this along the line time. And then you have, here you have a dxi, and this dxi in a sense, sorry, dxi here and it evolves here, right? Fair enough. So this is, of course, 4. I'm going to merely write it. That's why you find 3 plus 1, which is, of course, because it's 4. And now, if I write up the full 4-dimensional metric, I find that I can write it in the following way. So I have minus n squared dt squared plus hij. So the hij will be the metric on each leaf, right? And I have hij, and then it's dxi plus ni dt, and dxj plus nj dt. So basically, between these, the dxi here, and then how it will evolve in the following leaf, there would be an extra space-like vector ni taking you from one leaf to the next. And so you see you have the various relevant degrees of freedom. So this is the lapse. This is called the lapse function. So this is called the shift vector. And this is the induced metric, also called the first fundamental form of the discussion. Right. So now, of course, you have the full 4-dimensional metric written in terms of the 3-dimensional metric, and then you need to also look at the embedding of each leaf. And this embedding, sorry, I forgot to mention that there is also here, there is an n mu, which is orthogonal to the hypersurface here. And it actually, you can check it out by yourself, and it's 1 over n times 1 minus ni. As I said, you have to, this ni here comes from the fact that you have to propagate your dxi from one leaf to the next, right? And so now you complete the whole discussion with a second object, which is telling you how each leaf is embedded into the 4-dimensional spacetime, which is the extrinsic curvature. So this extrinsic curvature, it's called K. So I'm sorry, there are many Ks, in fact, Kij, which happens to be minus di. So when I have an I here, it's a 3-dimensional object only. And sorry, J and I. And when you gather all the things together, you find it is, is there? Okay, so that's di nj plus dj ni in terms of the shift vector minus d by dt of the first fundamental form. This is the second fundamental form in terms of the first fundamental form. And you see there is a time derivative, so it actually really tells you how the leaves are embedded in the 4-dimensional space. Now, with this construction, you're saying that the Einstein-Hilbert action I wrote earlier, now in these units, it's 1/2 only. So I have square root minus g d4x r. And then, so there is matter as well. Just in passing, there is an extra term normally, which is, so you're integrating over the full dimensional dm now. You're integrating at the surface of it, which will be square root h times the curvature here is 3x. dm is essentially sigma, right? Well, topologically speaking. And the funny thing is that this term, which is called the Gibbons-Hawking term, so it was written explicitly in this form. It was written explicitly in this form by Gibbons and Hawking in the 70s. But in fact, you can find it already in a completely different form. But when you gather all the terms, you find the same thing in Einstein's 1916 paper already. Right. And so anyway, normally you see you have this surface term, which is bothering. And in fact, in general, you just put it to 0 by assuming that you're working with a compact space. And there is, in fact, another reason why you would do that, that you can check that, in fact, all the probabilities are going to be normalized by something which is, roughly speaking, the exponential of the volume of your space. And so if you have something which is not compact, the volume is going to be infinite, and the exponential of infinite is also infinite, and you cannot do anything like that. That's one of the first problems you're having. So you restrict attention to a compact space, but it's not so much of a problem because it's just a normalization issue at the end of the day. Right. So now you can rewrite this action, assuming you have this drawing in mind. And now the 3+1 action can be written straightforwardly. I'm not saying simply, because it's a little bit complicated, but it's not that much. So you end up with the 3+1 Einstein-Hilbert action is now taking the following form. So it's an integral over time, and I specify time and I break explicitly these things. And then I have 1/2 integral d3x, and I have n square root of h. That comes from the square root of minus g to begin with. And it's kij minus k squared plus the 3 curvature, right? And then I have plus matter if I want, right? So this is the so-called, well, there are more than to that, but there's a listener ADM formulation. So you see, it's getting simpler now because you put it that essentially in the form of dl of dt, and then you have a gravitational Lagrangian plus a matter Lagrangian. Now you know that these Lagrangians, let's say, so my gravitational Lagrangian now is depending on hij, n, and ni. And then let's say that my matter Lagrangian, to simplify matter, depends on a field. It can be a scalar field, but it can also be a velocity potential, can be many things. Oh, I see there are some. Are there any questions? Okay, so the question was that canonical quantization give up covariance, but reparametrization invariance ensures general covariance of the theory. The answer is yes. Of course, this is still GR. So GR is covariant. Of course, that's the very idea of building GR to begin with. The problem, of course, is that when you do that, you don't have, you put space and time on unequal footings, which is the opposite of what you want to do in a Hamiltonian formulation. And you need a Hamiltonian formulation if you want to quantize your theory. So that's the idea, but that's absolutely it. You can, of course, at each step, you can reprove if you want covariance of the theory. Now, as soon as you have this formulation, you have a Lagrangian, and when you have a Lagrangian, then you can define canonical momenta. And in particular, so pi, where are the indices? Okay, ij is defined as usual by delta dl by d h dot ij. And you do the same, pi I equals dl by d n I dot, and pi 0 equals dl by d n, and you do the same with the scalar field if you want, right? And the first thing you see is that in kij here, or k squared, sorry, I forgot to say that k squared K is gamma ij, Kij, right? It was actually appearing here as well. Sorry, I should have introduced that earlier. Right. So, but basically, you remember that Kij is simply di. So that term contains di and j, essentially symmetrized, the half, or it depends how you symmetrize things, minus h dot ij. So it contains the h dot, which will come here, right? But you see that all these terms, none of them, I mean, the R3 metric is just a curvature, purely spatial thing. So nothing in here depends either on n dot nor n, which means that these things are constraints, the primary constraints, in fact. Right. So that's what you're having. And I think I'm now lost in my paper because everything went on the ground. I'm trying to recover things. Sorry. Okay. So now you remember when you're having a classical theory, which is the integral of a Lagrangian depending on, say, q and q dot. Then you define the momentum, or the momenta, if there are many of them, by dl dq dot. You perform the Legendre transformation, and you're saying, writing the h equals p q dot minus l, and you go on shell, and you find something depends, which depends only on q and p, right? Well, that's what you want, and you have a Hamiltonian, and normally then what you have this Hamiltonian, you can quantize it easily, put it into Schrödinger equation, and off you go. Now, this is exactly the same process we want to do here, so except that it's going to be a little bit more complicated because of this constraint, but you see you have the canonical momenta, and now you expand it in much the same way, except that now normally, you know, if you had like many of these indices, you would have PA. Okay, so that would be PA over here and QA over there. And now you would have a sum over A of PA, QA. But here it is an infinite number of, it's a smooth process. So now you have to replace that by a field. So this is actually going to be an integral, right? And so what you end up with by doing that is that you can define the Hamiltonian. This is exactly the same process. And now you define your Hamiltonian by being d3x instead of a sum. You see it's an integral over x of d3x. And so you have pi 0 n dot. This is exactly what I wrote here, plus pi I n dot I plus pi ij h dot ij minus the gravitational Lagrangian I wrote earlier, which I didn't write, but it's essentially this thing, right? You do that, and you apply you put that into the reaction, and you end up with the following: integral d3x. So that's, you find the same thing, and that plus pi n dot I plus, how can I write it? So you have n h plus n I h I. Right. So this h, I'm sorry, there are many h between the Hamiltonian and the Hubble and the horizon and all these things. Everything seems to start with an h. But now h is a kind of a local Hamiltonian density. And so you see, when you look at the equations for that, you find that, okay, so Ni is defined earlier, and Hi, where should I write it? Yeah, it's not going to be very comfortable. Right, so this Hi is simply equal to minus 2 root h bj pi ij, sorry, hi, yeah, okay, pi ij over root h, right? And the other one, this h here, shall I express it? Yes, okay. It's the most important, but it's complicated, but it's not that relevant anyway. So this h here is 1 over root h. So you have an hik hjl minus 1 of hij hkl, and then you have pi ij pi kl. Then you have minus square root h, and then the free curvature. Right. So you see, when you vary these equations, you know that you have the primary constraint. So this thing is 0, this thing is 0. And when you vary, well, essentially you end up with other constraints, which are this h goes to 0 weakly, right? Everything goes weakly to 0. That's defining the equation. And then you have the, where are they? Yes, so basically what you're having is one equation which is h equals 0, hi equals 0, plus the dynamical equation for hij, which I didn't write. And that is entirely equivalent to Einstein equation, right? So you have just a Hamiltonian formulation of GR. The thing is that so in quantum mechanics, basically, the dynamical equation for hij, that will be the trajectory equation, whereas the Hamiltonian is just defining the wave function. So let me see how it goes, because now we want to quantize all this. We have a Hamiltonian formulation, we have everything settled, we have the background, we have everything, right? So we can quantize the theory. So to quantize the theory, we need to, so what is needed to quantize is, first of all, the space of configuration, right? So when you quantize an ordinary particle in a potential, you're saying that the states, the possible states for a particle are, say, eigenstates of the position, right? So you're saying that, so you are having, say, a state, a position eigenstate, right? And then you can look at the wave function, and you're saying that the wave function is going to be essentially, when you project on these eigenstates, the state vector, whatever it is, and that gives you the wave function. Well, the idea here is to do, roughly speaking, the same thing. So in ordinary quantum mechanics, that was the state, these states. So now in the configuration space of quantum gravity, for gravity, the space, you have a configuration space, which is called superspace, that has absolutely nothing to do whatsoever with supersymmetry or this kind of super things. It's called superspace because I don't know why, but that's how it's called. And this configuration space is essentially defined to be the set of all possible hij of x, and say the scalar field or whatever it was that constituted your matter field, with x spanning your hypersurface. And of course, you have to quotient that with the diffeomorphism of sigma. By this, I just mean that you restrict attention to all these configurations that are in the same equivalence class as a given configuration. Meaning, for instance, if you write things in terms of Cartesian coordinates or spherical coordinates, is the same object that you're talking about. That's all what you're doing here. Right, and now you can define much the same idea. You can define a wave functional as, okay, I'm writing that in quote because it's not exactly correct from the point of view of mathematics, but it's to give the idea. So you have a wave functional like that, which is roughly speaking, when you pick up a state, Hij phi, and you project whatever wave functional you want it to have, right? So you see, you are in a very similar framework here. It's really, I'm writing that by analogy with ordinary quantum mechanics, but it's you shouldn't take that for granted. Okay, so now that I have that, when I have my theory here, as I said, for instance, I start with my Lagrangian, which is 1/2 mx dot squared plus d of x, right? Then I replace that. That gives me my Hamiltonian, which is p squared over 2m plus d of x, right? And then when I want to quantize, I take p, and I want to ensure that, you know, the ordinary Poisson bracket xp equals 1 is now replaced with the commutator xp. I've done this already. Xp equals I. There's an h bar here. And this is ensured à la Dirac, right? By stating that p equals minus I d by dx. Right? So this is the usual thing in ordinary quantum mechanics. Well, it suffices to do exactly the same thing here and put it in there. So we will assume the wave functional projected in the x representation, which is in the Hij representation. And so you can do that. So you'd say that phi ij is now equal to minus I d by d Hij, and the same d by dn I, and phi 0 goes minus I d by dn. And of course, you could have, if you had a scalar field, pi phi would be minus I d by d phi. You can actually go to, I mean, when you go to the scalar field, that's the standard process that leads to the Tomo-Nagashfinger equation. That's exactly the same thing here, right? There is absolutely nothing fancy here, right? Nothing's weird going on. So first of all, you can see that when you quantize your theory, the classical theory had a constraint, which was, I mean, you had two primary constraints, that these two things were weakly equal to 0. So you're saying that now phi, when it becomes an operator, I applied on psi is now, sorry, I should have, yeah, equals minus I d psi by d n I. And this is now 0. This is the equivalent of the classical equation. So you see that psi does not depend on ni. And similarly, pi 0 psi equals minus I d psi dn is also equal to 0. Which is why I restricted attention. Actually, there was some kind of a cheat in here because I restricted attention to phi depending only on the psi depending only on the scalar field or whatever it is that represents matter, and Hij, because I knew already that it doesn't depend neither on med nor ni. And indeed, they are not relevant degrees of freedom, and they correspond to the fact that you can pick up whatever kind of set of coordinates you want. Right? Now, the momentum constraint, if you remember, I had like this Hi equal to 0. That translates into, when you express it explicitly, dj delta psi by delta Hij equals, if you're now adding matter, T0i psi. So that's the stress energy tensor of matter. And that's just the basic constraint. And this actually means, this implies that all the configurations that are related, this is equivalent to saying that all the configuration, all the psi's that are related by coordinate transformation are just the same. So in a sense, this is automatically satisfied when you are in the configuration space as described here by because of this quotienting with the diffeomorphism. So this is automatically satisfied. And now I remain with the last constraint, which I just which I erased earlier, which was this one, right? So I now need to quantize that. If you have any question. Oh, I will not. Sorry, I didn't want to enter into these details. I would just want to. We can discuss that later if you want. But I want to really enter the quantization and show the importance for the bonds. It's really. I just want to concentrate on that. There was a question about primary, secondary constraints and all that. It's well, I'll go to that later. So anyway, what you where am I? Yeah. So you have this h equals 0. And now I can write it explicitly. I quantize that. And when I quantize, again, à la Dirac, what I'm saying is simply that I find this extremely complicated equation, which is h psi equals 0. Doesn't seem to be very complicated until you actually expand what that is, which is minus 2g I j k l delta squared by delta h I j delta h k l plus square root h, yeah, times minus r3 plus t00 psi equals 0. All of a sudden, it becomes a little bit more involved, especially when you know that this thing is jij is 1 over ijkl is 1 over 2 root h times I h I k h j l plus h I l h j k minus h I j k l. And that's called the width metric. This is telling you that the space of three-dimensional metric is in itself a six-dimensional metric with actually negative signature. So it's a Minkowskian kind of six-dimensional space, which induces a lot of issues. And of course, I should have said, but this is not very well defined, which is the reason why the whole thing is a little formal at this stage. In particular, because there are questions about factor orderings, which are actually also present in ordinary quantum mechanics, but which normally we just don't see them. What I'm saying is that you see, in particular, in quantum mechanics, when you have p squared, and when you have p squared in a classical theory, well, normally you replace that simply by the operator p squared, right? Although when you think of it, nothing prevents you from stating that of replacing it by, I don't know, something like x p x to the minus 2 p x. You see, this is symmetric. And classically speaking, it's exactly the same as that. Except that quantum mechanically speaking, if you put that in your Hamiltonian and in your Schrödinger equation, you get a completely different result. So there is already a factor ordering issue. And in particular, this factor ordering, basically, how you solve it is that you pick up the classical theory, you quantize it one way or the other, and there are essentially a very large number of ways to do that. And then you compare with the actual data. And then you decide what was the correct factor ordering, which of course you can do in ordinary quantum mechanics. You cannot do that for quantum gravity because at the moment we don't have any data. But then you see, otherwise you have this equation, forgetting about the fact that it's ill-defined. It's called the width equation, and it looks simple. When you forget about this expansion, it looks very simple. It's actually, when you think of it, it's a timeless Schrödinger equation. And the fact that there is no time is actually an issue here, but I will not go into that. And okay, so that's the general framework, which of course is essentially inapplicable in general. But I will try to convince you that it's not completely lacking interest anyway, because by taking an example, right? And let me assume, so let's forget about all these things, all these complications. I wanted to go into these complications to show you that it is not just a game that we are saying quantization permits to solve that and that problem. It actually does, and I wanted to show you a specific example, which is, well, essentially sufficiently well defined that we can discuss it in full details. And well, it's not as bad, and well, it's not as complicated as other models like string theory or whatever. So once you have that, now let me pick up the example where matter is that of a scalar field, right? And then basically what I have is a pressure term, which depends, say, on the equation of state, which I will assume to be, say, constant to simplify matters. And this now phi is potential, is a velocity potential. Right. So I want, yes, in general, the Euler-Lewis equation, you can't solve it, but then there are situations where you can actually say something. You may not solve it in general, but there are situations where you can solve it. So I said that the space of configuration was the superspace, and the superspace has all the relevant degrees of freedom, right? And it's a continuous infinity of terms, right? Well, the idea is to try to reduce that to something which is called a mini superspace, where you now replace the full metric by, say, ds squared equals, so you stick with minus n squared dt squared, because that gives you some interest. So let me just write it in a different way. Now I'm going to be using d tau squared in general. Restricting, when I go to cosmology, I will restrict attention to t being the cosmic time, really. And then plus a squared of tau, and then, okay, the x squared, whatever that is, right? That may also include curvature, spatial curvature, right? And so now I've restricted attention. I have this continuous infinity of term hij, which have been now replaced with one single degree of freedom. And similarly, phi, which depends on psi and tau, now depends on me, on tau. So basically, I had an infinite number of degrees of freedom, and I have 2 at the end. So I will end up with a wave functional now depending on a and phi, which is quite cool. So I have that, and I take the all the machinery I discussed earlier, and I do the detailed calculation, and I end up with the following, right? I need to do a few chemical transformation in the middle of the way, but I end up with the following thing, which I have n minus pa squared over a, over 4a in principle, minus the curvature times a plus pt over a to the 3w. Right. So first I see that there is a pt here now. This is linear. I have done a few canonical transformation. I started from phi equals to a variable which is now t, called t, right, capital T. And you see that I have a term which is linear in my Hamiltonian. So you may be tempted to think, well, hang on, if I have a linear term in the Hamiltonian, the energy is not bounded from below, which could be a problem. So one way to think about that is to think in terms of clock, rather than time. And you see, well, hang on, I take this n here, and I have this a to the 3w. So the natural choice would be to set n equals a to the 3w. Because if I do that, then automatically I cancel this term. And now I end up with a h. You see, my final Hamiltonian becomes say I have an H which contains the first two terms. I don't know how to call that. Let's say A plus PT, right? And now that's pretty fun because when I quantize, okay, PA will be quantized. As I said, there is the factor ordering. What is PA squared over A? Not clear. I can put the A one way or the other. KA is fine. And then, so when I quantize that, I end up, as I said, with the Wheeler-DeWitt equation, which is H psi equals 0. Okay, and now this is equals to H A psi plus, now what is PT? Well, PT is a la Dirac quantization minus I d by dt psi. And now from my timeless Schrödinger equation, I end up with exactly the right thing, which is a time-dependent Schrödinger equation. So now T here, and I remind you, T is coming from the perfect fluid. So in quantum gravity as well, quantum cosmology in that case, as well as in ordinary general relativity, time is defined again by the fluid. That's why it's called a clock rather than a time, because it's an external object to GR. So I define the time Schrödinger equation. So now let me pick a specific case, right? Very simple. You see, at the end of the day, I only have HA. Let me assume that, say, I said K equals 0, and I define X equals A to the 3/2 1 minus W. As it turns out, that simplifies this. You see this 3W plus 1, you see where it comes from, or minus 1, sorry. And you can reshuffle the terms and all that, and you end up with an equation which is I d psi by dt equals a quarter d2 psi by dx squared. And you see the great thing here is that you start with a horrendously complicated Wheeler-DeWitt equation describing whatever space-time, and you end up with a Schrödinger equation, time-dependent Schrödinger equation for a free particle with not even a potential. This is pretty cool because you can solve that explicitly, right? And so you do that, you solve this equation, and what you find is that the wave function is now an amplitude depending on this x and my time variable times an exponential times a phase depending on the same thing. So the amplitude, I can give it to you, it's proportional to square root 1 plus t over t0. There are integration constants coming here, exponential minus t0 x squared over t0 squared plus t squared. So it's kind of a Gaussian amplitude, and then the phase is actually, okay, it's irrelevant, but never mind, plus tx squared over t squared plus t0 squared, right? Sorry, plus arctan t0 over t, right? Anyway, so you have something, you have a wave function for your universe. And now there are many things. I don't know how much time do I have left. Am I done already, or was I supposed to stop?
You're almost done, Patrick. You're almost done with your time.
Okay, so I will finish here today with that. Unless you want me to keep going, I can go on for a couple of hours more if you need. But okay, now the thing is the following. Once you have the wave function, basically it's always a bit complicated to say what is the meaning of the wave function of the universe. Basically, we all know that in quantum mechanics, the wave, we know that psi square is the probability of observing this and that, and it's not very clear. Now, in the case at hand, remember the Hamiltonian was essentially p squared, right? I forget about the other terms. Sorry, this by a. Okay, that was the Hamiltonian. So that classically speaking, I know what is the equation. I know the equations of motion. I can write them. I can solve them. And basically, I can write the phase space, right? A pi A. And pi A, classically speaking, in that case, is roughly speaking the Hubble scale, right? And so I have solutions which are pi A equals constant. So basically, the solutions I find are that. So I find solutions that are, sorry, I shouldn't have done that. Either contracting towards a singularity or expanding from a singularity. So this is the classical situation we're living in. So this is another classical situation where some other universe may end up being in, right? And so now what you can say with this particular wave function in particular, you can say, okay, let's imagine that I have a state which comes from a classical configuration. And with this wave function, I can calculate the probability to go from this to say this one. Of course, I can't tell you anything about what is happening here, but I can calculate a non-vanishing probability to go from a contracting to an expanding universe. Somehow that's what I want to do. That's the way I want to solve the singularity problem, right? The second thing this is one way to solving the problem by thinking in terms of psi as giving me probability amplitudes or probability densities, one way or another, right? Another way to do that is to say, well, okay, I can look at, now that I have my wave function, I can say, well, maybe I can make sense of, I don't know, I can calculate in this the absolute, the expectation value of x, which as I said here is roughly speaking the scale factor. So by playing with that, I can give x, and then I can do the same with px, right? And then I can plot them. I can give like a or pa, right? The expectation values, and I can plot them. And that's where it's becoming funny, because all of a sudden you find that something is which is classical, and then you join smoothly to the other configuration. And of course, when this is in phase space, but then nothing prevents you, since we have a time now, it has been more or less defined, nothing prevents you to write what it is as a function of time, and then you write, say, A, give you a bounce, which is which is exactly the one whose envelope is the classical theory. And so you see these straight lines correspond to this one going all the way to the singularity, this one coming from the singularity, that's this one here and that one here. And so you just connect smoothly the thing. And the funny thing is that you can do that for many other operators. You can think of A directly, or you can plot, for instance, square root of a square, that would be the variance somehow of the scale factor, or you can find trajectories. I'm not going to enter into these, but you can find other kind of trajectories like the Breuer-Bohm trajectories or coherent state approach trajectories, or these kind of things. And for all of them, essentially, you find the same kind of things. And more interesting than that is that you can find one trajectory, another one, another whole set of trajectories, and they can be really like kind of weird things if you want. I could show you. We obtained recently these very bizarre kind of trajectories, but the semi-classical limit is always the same. So we can hope, we haven't done that yet, but we can hope that whatever happens in the classical regime or in the semi-classical contracting regime can be propagated using quantum effects in a way which is going to be like in a one-to-one correspondence to that. So in that sense, we have, you may reproduce a fully quantum model that will give you exactly what you want and produce some predictive theory. Now, I wanted to finish, if I just have one more minute. If I don't know if I have one more minute, because I have no answer from Sriram, but hoping in the lack of answer.
Maybe we should wind up, because we have the next lecture in 20 minutes.
Sorry. Okay.
Just need a bit of a break and allows, if someone has a question or two.
Okay.
Are there any questions for Patrick? There is one hand that has been raised. Yeah, let me just. Hi, Sergey. You should be able to speak up now. Can you
Hello.
state your question?
Can you hear me?
Yes. Yes, we can.
Great. Thank you very much. I wanted to ask if there are any issues with the way you introduce time.
There are loads of issues with the way I introduce time, and there are actually books written on this on the matter. This is one way of deparametrizing the Hamiltonian here. It's one way of doing. Actually, there is a more fundamental issue, which is that, in particular, the Willard-Witt equation is a timeless equation. So you need to introduce time one way or the other. That's the problem. Of course, anytime you introduce one time, sorry for the repetition of the word time, but each time you introduce some clock, you make some approximation or you make some hypothesis, basically. So nothing is really clear. But as I said, when you think of it, quantum mechanics does, roughly speaking, the same. You see, in quantum mechanics, there is no such thing as a time operator, right? And you assume that there is an external time. But when you think of it, what is this external time? Some people believe that it is the same as in the Willard-Witt case. Basically, you have no time, but then you are using a clock, which is an external object on which you count. Like say, okay, you pick like a bunch of radioactive particles and you just count the number of decays, and then that tells you a unit of time. And then you solve your Schrödinger equation with this particular time. But you see, it's a clock thing rather than a time. And we do the same here. At the end of the day, you should check that it is indeed time reparametrization invariant. That's exactly, actually, thank you for the question, because that's one way of solving the question of time. I mentioned the Broglie-Bohm trajectories here in particular. You can check that these trajectories are reparametrization invariant, really, so that the four-dimensional space-time you have reproduced is not just two bits of space-time which you just crunch together, but it's actually a full, real four-dimensional space-time that makes sense. Was I clear?
Okay, are there any other questions? There doesn't seem to be any other questions. There is one. Yeah, let me just unmute. Hi, Noel. Can you proceed with your question?
Yeah, I just wanted to ask about how do you know if the transition is smooth? I wasn't quite clear about that. You say that there is a smooth transition, but quantum mechanically, that's not really the case. So we don't really know what happens.
Absolutely. Yes. So when I'm saying the transition is smooth, I was referring to, I pick expectation values of operators.
Okay.
Yeah. Right. I pick the expectation values of operators. They are defined really as an integral, you see, like psi star A, psi dA or something like that. And I integrate that. Okay. And that gives me a function of time. Okay. And this function of time is the thing which I plotted here. Now, I may not want to do that because I know people don't like trajectories in quantum mechanics, but that's why I was saying, without the smoothing effect which I have here, I can always assume that there is some sort of a transition amplitude from the decaying to the from the contracting to the expanding universe, and that I can calculate by using psi square being the probability from one thing to the next, like in ordinary quantum mechanics. You have one state here. Basically, you have a psi in, and then you have a psi out. And then you can calculate the probability of connecting one to the other.
And how do you choose the two states?
There are various possibilities of doing that. One of them is to use coherent states in particular. because they are getting as close as, but you can pick, I mean, there are various possibilities, but one of them is, as I said, you can use coherent states which satisfy a classical equation.
Okay.
Whose, okay, I could not enter into the details of it, but there are various ways, and I can give some reference if you want. I can send Sriram a few references, which maybe they can be put somewhere in the Slack file or something.
You can use the Slack channels, Patrick.
Yes.
You can leave the references.
I will do that. Yes.
All right. Okay, I don't see any other questions, Patrick, but I'm sure there may be, some in the next lecture and in the tutorials. Thank you for joining us today, and we'll see you tomorrow.
Yeah, sure. See you tomorrow.
Thank you.